I am pleased to welcome Cheryl Palmer to our eCOTS 2020 session. Her title of our presentation is The Evolution of Regression with Minitab. A little bit about Cheryl. As a Minitab trainer and statistical consultant, Cheryl is immersed in the day-to-day problems faced by practitioners. Drawing on more than 25 years of experience and teaching statistical consulting and software development, Cheryl aims to provide the sound statistical strategies and software tools that professionals need to solve the real-world problems they face on the job. She has worked on the project teams that developed many of Minitab's most popular features, including Assistant, Design of Experiments, Gauge R&R, and Reliability. She was also one of the developers of Minitab's online learning solution, Quality Trainer. Please take it away, Cheryl.
Thank you for having me. So I'm going to make sure we get this right. Take you over to Minitab, and I think, here we go. I wanted to talk a little bit today about how things have changed with Minitab. Specifically, we have added some more in the area of predictive analytics, particularly with Minitab 2019 version 2020. So this is available both on Mac and on PC. But I wanted to talk a little bit about how things have evolved quite a bit in the world of just observational data, so to speak. We have, for many years been teaching students all about regression and logistic regression for problems like the one we're going to talk about today. So today I have, hopefully you can see some of the data. This was data from, changed a little bit, but from a manufacturing plant that manufactures glass. And they manufacture glass for various markets: the beer market, the wine market, the beverage market, the pharmaceutical market, etc. But one of the problems they needed to solve was they needed to look at these specific predictor variables: color, plant, where it was manufactured, the weight of the bottle, how many cavities the mold had, the speed, efficiency, setup time for actually setting up to be able to deliver the product. The amount of energy used, all of that affects the cost of manufacture for the final product. And that's what they do. They're always creating final product for various customers in these different industries. And being able to estimate the cost is really, really important so they can quote the right cost to the customer. So this is one of those data sets that I had actually gotten several years ago before I had really started learning about machine learning and some of the new tools or newer tools that are really great for handling observational data like this. So if you look at this, you have a response cost, you have 9 predictors, standard old regression model, stat, regression, fit regression model. I'll put in cost. My categorical predictors are the color of the glass, the manufacturing plant it came from, the market segment, and then I'll add to it the weight, the number of cavities, the speed, efficiency, setup time, and energy use. Now, a few things. This is a larger data set, so here's just a little tip and trick for you. With larger data sets, you may want to turn off the fits and diagnostics table. This table uses anything that has a standardized residual smaller than -2 or higher than +2 as flagging it as unusual. With larger data sets, well, with any data set, that means about 5% of your observations should be flagged unusual just because of the rules around normality. So with a larger data set, if we're flagging 5% of those observations, that table gets huge. So I often actually turn that off now that I have been working more with larger data sets. I do want to point out a few other nice things that we do in regression that I find really useful. In coding, a lot of times standardizing predictors helps reduce multicollinearity to some extent. So I do actually often standardize my predictors. And then 2 new things that came with this release of Minitab, release 19 version 2020, are validation. So validation is something that many of you, I'm sure, have heard of. The idea of holding out, especially with these larger data sets, hold out some of your data, fit the model with data we call trained data, a portion of your data, and then see how well it fits for the held out data. So with this release of Minitab, we have added validation to regression and binary logistic regression. We've added 2 types of validation. We've added k-fold cross-validation, which means that we're going to divide the data into k random folds, fit the data on all but the kth fold, and then use the kth fold to, as a holdout. And then we'll do it with, so in this case, I'm using k as being 10. So I'll fit the data on 90%. I'll fit my model on 90% of my data. I'm holding out my 10th fold or 10% of my data. And then I'll see how well that data fits for that held out data. And then I'm going to rotate through all 10 folds. So every data point will end up being in both the training data set and the test data set. So if you haven't seen that before, k-fold cross-validation is pretty cool. We can also do pure validation with the test set, meaning just hold out 30% of my data, for example, at random. I'm going to create the model with the remaining 70% and just see how well it fits for the 30% I held out completely. So k-fold rotates through the data. Just using a test set just completely separates it. But one thing we did in addition to that is in our stepwise, we've added the ability to actually stepwise based on validation. So we have the usual stepwise criteria, stepwise, forward selection, backward elimination based on p-values. But in these days, p-values are becoming a little less popular for model selection. So it's a little starting to be a little more common to select models with either information criteria, which we added a few releases ago, or I like this one, forward selection with validation, where I can either hold out a certain percentage into a trained test, or I can use that k-fold method to rotate data points in and out of my test and train set. The question just came, how many observations do I have here? I think I have around almost 10,000. I have 9,000 something. So I'll show you how to quickly get that information as well from Minitab. So I'm going to go ahead and use k-fold cross-validation, forward selection with validation on this data. And because I will get what will probably be my final model, I'm going to go ahead and turn on the residual plots. It'll take a little bit to run because it's running 10 different models, each one on 90% of the data. Here are my results. To find out exactly how many data points here's another little tip and trick for you. If you right-click on the worksheet tab and choose worksheet information, that actually tells you really quickly what's in that worksheet. So we have 9,487 observations here. So let's see what happened. We get kind of a messy model, but I did standardize my data before my continuous observations. So that tends to keep my VIFs a little bit lower, so a little less variance inflation. Although I selected the model without actually worrying about p-values. The way I had Minitab select the model was to find the model that had the best tenfold R squared. And so that tenfold R squared is data that is being held out. We're calculating the sums of squares error for held out data at every run, and then using that to create a R squared measure based on the held out data. So this model actually fits pretty well. We can see we get a nice plot here of looking at the model selection steps, and we see that we get to about step 6 or 7 of the 9 predictors. Now this was just a linear model. I didn't add interaction or polynomial terms, but in this kind of simple model, it looks like we get to about 5 predictors, and things kind of start to level off in terms of what we need in the data, but the best model did end up using all 9 predictors. So, but you can see, again, at some point, your R squared for tenfold stepwise, so basically your R squared test does start to kind of level off. So you may not need to use those additional predictors if you don't want to. But that's become a little more popular for modern model selection. People aren't using p-values all the time anymore. It does turn out that all of these predictors were significant, some of them certainly much more significant than others. For example, the weight of the glass bottle was very significant. But the problem we end up with regression, and if you think about, if I had added this one, I have some categorical variables in, so I have a pretty large table of coefficients. If I had also added things like interactions and polynomials, I would end up with a lot of significant p-values that things might get a little bit trickier to start interpreting. So one problem that regression falls into, especially with even larger data sets, is almost everything ends up being significant because you have tests that are kind of too powerful. So that's part of why p-values have become a little less popular in some of the predictive modeling that people are doing today. The other problem is as you look at observational process data, particularly as your data sets get larger, you are likely to see things like this. This is not a good thing. This is not a textbook example. And so my residual plots don't look so great. I have some extreme outliers. I have inherently messy data, which is actually very common as you're looking at observational data, larger data sets. The other thing you run into, and this is true here, is you can end up with a fair number of missing values. And in this data, I know there's one column in particular, I think it's the cavity column, that has a whole bunch of missing values in it. With regression, it's just going to throw away those rows with missing values. Whereas when we start looking at classification and regression trees, they have a really nice way to handle them. Basically, what they're going to do is find another variable that can be what they call a surrogate that takes the place of the variable that has a missing value. So let's see what happens with this data when we use a CART tree. This is CART regression because my response variable is continuous. And choose the CART regression model. Continuous predictors, categorical predictors. Oops, I forgot energy use. That was a continuous one, I think. Yep. One thing you will notice as we start creating new dialog boxes in Minitab, we're starting to focus a lot more on ease of use. When I filled out my continuous predictors and then went down to my categorical predictors, it filtered out the ones I'd already used, so I didn't have to find them over on the left side in the selection list. Love that. Validation, same thing. We can do validation with a test set, or we can do k-fold cross-validation. I'm going to use validation with a test set this time, and I'll hold out 30% of my observations at random. And I am going to go ahead and just run this. So we get the same kind of information that we did with regression in terms of looking at a test R-squared. So here we see that our CART tree, my test R-squared was about 81%. I could do a little better if I go a little further out on that tree. One thing we are doing is creating somewhat simpler trees. We're not actually using in CART the maximum test R-squared test. We're actually using the test R-squared that is within one standard deviation of the maximum test R-squared to pick our what we call our optimal model. The reason for that is you'll end up with simpler models, and CART does tend to overfit a bit. But if I want to, I can actually create any of these other models as well, or even a simpler model. So if I want to create a really simple model, I can just go down to the bottom of this plot. It has a much lower R-squared test of 0.419. But if I just wanted to demonstrate a CART tree, it's going to be a much smaller CART tree to show my students. So here is a very, very simple CART model, and you can see how CART works with this model. What CART is going to do is partition my data into high and low values. And it turns out, I'm not surprised by this because weight was the most significant predictor when I looked at the data through regression. Now, as I look at it through CART, it ends up being the first split. So if I split my data just at weight being 445 or 446, if it's less than that value, my average ended up being 101. in terms of the cost. I'm not sure what those units are. There's some kind of standardized unit. My average, if my weight of the glass happened to be above 446, the average goes all the way up to 203. So this is a very, very powerful predictor to be able to split my data on. And that's what CART's going to do. It's going to split left and right into high and low values of the response. So my overall response mean, by the way, my mean cost was 138.3, and with just one predictor, I've split it into low ones and high ones. So one thing I love about CART is that nice visual. Now I'm going to go back to the optimal tree. Sometimes these optimal trees do get a bit messy. They get large, but we can see this data keeps splitting and splitting and splitting. One suggestion I have, and I have found really helpful when I start looking at these large trees, we can focus in and teach our students, how that splitting works. But if we want some overall results, one thing that you can do is you can save the predicted values and also save what's called the terminal nodes. So as things observations fall through this tree, they end up in nodes. And if I actually save these final nodes that are combinations of predictor settings that things have fallen through, I can actually create some nice graphics around that are a little bit easier to read than this gigantic CART tree. So I'll show you a few of those here. But this one, after the first weight split, if the weight was low, the next split ends up being on speed. So high speed versus low speed. And then it splits on speed again. And we can follow each of these nodes, different places, or follow each of these branches of the tree to see where all the splits are. So you can see different splits happening in different places in this particular tree. But my optimal tree ended up having 25 nodes in it. I could actually even, again, in that first plot, I could create an even bigger tree if I wanted to and get the true optimal rather than the one standard deviation optimal. So I could also say, you know what, I want the one with the absolute maximum R squared test. It'll give me a much higher well, not a much higher, but a reasonably higher R squared, but it'll end up having 986 terminal nodes in it, as opposed to the one standard deviation tree, which was nice because it was quite a bit simpler. So, but this is another thing that's kind of nice to play with and show trees of different sizes, so you can kind of explain how the trees work. So now I'm going to go back and I'm going to recreate this tree, but I'm going to store some statistics in here. I'm going to go to storage and store the terminal node ID as well as the fit, because then I can use those values to actually create some really nice graphics. Okay. So this just stores the terminal node and the fits in my data window. And I can do things like find out how that fit changes in those different terminal nodes. So I'm going to go to just a simple scatter plot here. And I'm going to look at as my Y what the CART model predicts versus what node things landed in. This is really helpful because I can see here that I have, some terminal nodes that have particularly high values. And I might want to, these were the outliers that were showing up when I ran the regression. So these are some things I might want to investigate. Now I can use Minitab brushing to easily investigate what's going on in these nodes. So I can, for example, select this one. It had particularly high fits. And these all came from this is one terminal node. So this is terminal node 6. There weren't a lot of observations in terminal node 6, but let's find out more about them. So I can add here all the other variables and see why the fitted value, which in this case is the average cost for that specific node, why it was so much higher than usual. So once I didn't mean to do that. Once I add these additional variables, let me click select, click OK. They show up over here on the right side of my screen, and I can see if there's any patterns. So these ones that had high cost, what can we see about them? Well, they all had efficiency of 88, Their speed varied a little bit. We can look at their weight relative to the rest of the observations in the sample. They all happen to be the same color, so that's kind of interesting. I can see some other things if I want to look at all these high values and see things like, did they all come from a specific manufacturing plant? So in all these cases where we get predictors that are quite a bit high, meaning I have manufacturing costs that are high, I want to know more about them. Where did they come from? And that's what I'm getting as I brush these fits versus the terminal nodes they came from. So I see that there's certain colors that stand out. Cobalt comes out a little bit more. Plant 13, I think, stands out a little bit more. Wine tended to be a segment that ended up with slightly higher costs. It's interesting when we look at weight. We knew weight was really important, and if you look at these values of weight, and we can actually do some graphs around these, but when I look at these values of weight, I see that they're all high except for these ones that are only around 360. So one of these terminal nodes, it was this one right here, the weight actually was low. In every other case, when we had really high predicted values, the weight was actually really high, like in the thousands. Here, the weight was only in the 300s. So really interesting information that I'm going to start using some graphs to investigate further to find out, especially about these specific terminal nodes that, let's look at, for example, terminal node 6. I can use that as a grouping variable. Oh, and I'll do one other thing. When you brush, you can also set grouping variables through brushing. So I can, let's say, focus on this group of anomalies. And I'm not, again, not a lot of observations in that group, but let's focus on that group. I can turn on indicator variables and create an indicator variable for this particular group, which was group 6, terminal node 6. And I'm going to code my brushed points as 1. I'm just going to do this one time, update now. And now I have a new variable that represents in my worksheet whether something's from group 6 or not. That's nice because then I can look at things by that group. So I can look at relationships, for example, scatter or a matrix plot of the different either fitted values, or I'll just use the raw cost in this case. I'm going to use all of these continuous variables by cost. Oops, what did I leave out? Select. I'm going to, under matrix option, just look at the lower left so it's simpler. I could have used fitted values as well. I'm using the raw values here. But what I'm interested in is if I'll be able to see whether where group 6 falls in this. Now, group 6 wasn't a lot of points, so it might be a little bit difficult to see, but what I can do is I can actually change my symbols. I can do things like make them smaller, I can make them clear, I can make them, I like the diamonds like that, and make them, in general, a lighter color, but then I'll add a grouping variable that will be a darker color and stand out a little more. So there's things we can do to play with the graph if we need to. But we can see where they are. We see these were values. They came from a specific number of cavities. This is where the cost was high, right? So any place it's red in here is that where that terminal node that had really high predicted costs fell in some of these variables. And you can kind of look at that. They were low for weight, which was surprising because in general, we have a really strong positive relationship with weight. But for that particular set of atypicals, in general, they tended to have lower weights. So it's interesting to see how those unusual observations kind of played out in the model, and we can do a variety of graphs around that. We can also look at things like, let's do some bar charts of that. So I want to do bar charts that compare things like what segments we came from. So I'm going to do a bar chart of, let's see, I'm going to check this out in separate panels of just, I thought, you know, what segment, market segment it came from, and maybe what color. And I'm going to go to multiple graphs and separate into separate panels by whether it's in group 6 or not. And so then I get a nice comparison of one terminal node, and this one doesn't work great because there's only a few observations in here, so I actually might want more of those high values. Sorry, I should have done that first. But this is a way you can get nice comparisons between, you know, most of your data and then those weird data points, right? So if I go back and do some more brushing on this plot, I want to look at all of them, all of these groups that had really high fitted values and investigate some more information around them. So not just that one weird one that only had a few values. If we look at all of these, so these were high cost ones. Again, I can set an ID variable that will be my new grouping variable. These are all ones with high fitted cost. And I can look at, oops, I don't want that. I'll just say high cost. What am I doing? I set ID variable. Sorry, I want to set the indicator variable. That's what's going wrong. Set indicator variable for high cost. There we go. And now I can look at a larger set of variables that ended up having higher cost and look at them in various graphs. So really nice ways to kind of explore what was happening in my CART model. So I'm going to create that bar chart again. And one thing I can do is go back to the bar chart I have and just say, I want to make a similar graph, but this time I want to use, instead of just looking at group 6, I want to look at everything that was high cost. Still fairly small number of observations, so a little bit hard to see in this graph, but if we don't split it quite as much, let's do a bar chart of just the simple variables, so I'm not splitting things up, and just look at color, for example. And again, under multiple graphs by those that had high costs. That one. We see that they're kind of spanning the whole gamut in terms of their color. Here's another trick for you. You can color code bars. That just makes them prettier just by assigning groups to bars. So there were certain bars that stood out and certain colors that didn't exist in those groups that had higher cost associated with them. We can also, because there's so many observations that fall in the general public, to separate these out, we can also just split our worksheet and separate out by whether that was a high cost or a low cost variable. And the reason why I might want to do that is the ones that had high costs, there just weren't as many of them. I can right click and look at worksheet information and see this is only 30 observations. I'm comparing them to a group with a much larger number of observations, but I can do graphs this way and then compare them to the same graph with the other data. So I'm going to go back to bar chart again. We'll do this. Now look at color, where I've just separated out these 30, and that pops out those bars, so I can see they happened with 4 colors in particular. And I can go back and see overall my data. Most of the data was flint in color. In terms of my defects, or ones that had high cost, how they tended to be cobalt. Cobalt over here almost doesn't stand out. So a high proportion of cobalt, for example, end up being higher cost. So all kinds of ways that we can explore. That gave you a quick check. Did we have any questions? Sorry, we're out of time. Boy, time flies.
Yes, we do have a couple of questions. Thank you much for your talk. First of all, I remember you saying that this was, I believe, Minitab version 19 in 2020.
Yes.
Is that correct?
Yes.
And that is the standard version of Minitab that would be available to students?
Yes. Yep.
Great.
So 19-20-20 added the validation that you saw as well as CART.
Okay. And how does Minitab facilitate student report writing, such as putting output into dynamic documents?
So usually the easiest thing is just copying and pasting. You can send directly to Word or PowerPoint. We don't have a link to Google Docs right now. A lot of times it's just easier copying and pasting.
And is this data set available so that people could use it in the classroom, or?
Yeah, sure. So let me put up my contact information. The best way to do that would be to email me. Let me see if I can, easy. But you can contact Minitab directly. Here are some information about and if you just contact academic sales and just request for this data set, Nicole, I know our academic salesperson is on the line right now. She'll make sure that we get that to you. So I will make sure academic sales has that. And yeah, I'm happy to share that.
Great, thank you very, very much. I appreciate you coming and sharing Minitab with us.
Yeah, thank you for having me.
You're welcome. So thank you, everyone. So now we are going to take our break for our session.